Hello everyone, welcome to this presentation. Today we are going to talk about electromagnetic radiation, something so well known but also so well unknown. So in this presentation we are going to talk about the origin of electromagnetic radiation. In this presentation we will see first an introduction, then the basic equations will be revisited. We will study the fields created by a charge in motion. Also, we will study the behavior of oscillatory charges. Then we will show how to calculate the radiated energy density and power from an oscillatory charge. And finally, we will talk about the momentum of light. Most of the content of this presentation has been obtained from this reference, the Feynman Lectures on Physics, Volume 1. We all know and have heard about electromagnetic radiation. The electromagnetic radiation is emitted in the form of waves, as we know, and these waves are characterized by two main parameters. One is the wavelength, lambda, of the wave, usually measured in meters, and the other one is the frequency, measured in hertz. So if we go from low frequency to high frequencies, then we will have at low frequencies radio waves. Then if we increase the frequency, go into the microwave range, then infrared range, then we enter into the visible part of the spectrum that we can see with our eyes. Then we increase further the frequency and get into the ultraviolet range, then X-rays, and finally gamma rays. The same classification can be made using the wavelength of the radiation. So if the frequency is low, the wavelength is going to be high, and then when we decrease the wavelength, then we are going from radio waves up to gamma rays. Another important parameter that characterizes the electromagnetic radiation is the energy, and we know also that the energy is proportional to the frequency, and the constant of proportionality is h, which is the Planck constant. So we know that the higher the frequency, the higher the energy that is transported by the radiation. We also know about examples of sources of radiation. For example, we know that antennas can generate radio waves that are useful for communications. And also another source of radiation is a lamp, for example, an incandescent lamp, in which when we heat up metal, then the metal is going to generate radiation, mainly in the infrared part of the spectrum, but also in the visible part of the spectrum, and even a little bit in the ultraviolet region of the electromagnetic spectrum. So, okay, we know all this and we take electromagnetic radiation for granted. But if we think about it, we can ask ourselves two questions. First is, what exactly is electromagnetic radiation? And how is electromagnetic radiation ultimately generated? These are the questions that we will try to answer in this presentation. For starters, we are going to recall the basic laws of electric fields. We know that if we have two charges at a given distance, as shown here in this image, then we are going to have a force between them that is given by the Coulomb's law. So we have this constant here where epsilon 0 is the permittivity of free space. Then we have that the force is proportional to the product of both charges, and inversely proportional to the distance squared, and the direction of the force is given by this unit vector E sub r that we are showing here in this schematic. In this case, we are assuming that both charges are static, so they are somehow glued to the position at which they are, so they cannot move, because otherwise the force exerted on the charges is going to move them, and then we will have another behavior, as we are going to see later. So if we consider a lonely charge Q as we are showing here, we can say that this charge is doing something in the surroundings, because when there is no charge there is no effect on other charges. But if we have this charge Q, then we know that if we place another charge here at a given point P, then there is going to be a force exerted on it. So this something that is surrounding this charge Q is known as the electric field. And the electric field is characterized by its intensity. E. The intensity of the field, as we know, is a vector which is given by the force divided by the charge. So is the force per unit charge that we have at a given point. And then dividing by Q, we have this expression for the electric field intensity that we all know very well. Another very important aspect of electromagnetic fields is the superposition principle. So if we have one, two, or several charges, as shown here, Q1 and Q2, and we want to calculate at a given point the electric field that we are going to have, we only have to apply the superposition principle and add the electric fields created by each of the charges separately, add them together, and then we will get the total electric field at this point. So this is very important principle, and it can also be applied not only to electric fields but also to the magnetic field. Note that up to now we have only talked about static charges and electric fields, because there is no magnetic field generated by static charges. The magnetic field can only be generated by charges that are moving. And when charges are moving, then things are getting much more interesting. So let's study what is the expression to calculate the field created by a charge in motion. We have here our particle that is going to move along a given trajectory, any general movement, and we want to calculate the electric and magnetic fields that we are going to have at a given point P here and at a given instant T. The first thing that we have to consider in order to have a general expression is that if we want to calculate the electric and magnetic fields at this point at instant t, we have to consider not the position of the particle at the same instant t, but the position of the particle at the instant at which the radiation was emitted from the particle, which is the time instant t minus the distance divided by the speed of light, the speed of the radiation. So this is very important to understand the behavior of the electromagnetic radiation. In fact, it is impossible for us to know at a given instant t where is the position of the particle at this same instant, because we need a time to get the information from the particle to our point P. This is something that we can understand, for example, in the case of the Sun. If we look at the Sun, we are seeing the position of the Sun not at this instant, but where the Sun was something like 8 minutes before this instant, because the light from the Sun needs around 8 minutes to travel from the Sun to the Earth. So the position of the charge at this instant, t minus r over c, is known as the retarded position. And then if we go to the literature, we can find this expression here for the electric field that is going to be generated by this charge in motion. So we have, as we know, this constant here, and then we have three different components. The first component is related to the position of the charge. As we see here, this is something similar to the Coulomb's law. So if the charge is static, we only have this term here. But then when the charge is moving, we have another term here which is related to the velocity of the charge, because its derivative is the derivative in time of the position vector er. So is something related to the velocity. And finally, we have this other term here, which is related to the acceleration of the particle, because is the second derivative with respect to the time twice of the position vector of the particle. Finally, if we are interested also in obtaining the value of the magnetic field, then we can use this expression here, which is the cross product of the position vector, the unit position vector, and the electric field divided by the speed of light. Now let's analyze this expression of the electric field carefully. For this, we are going to evaluate qualitatively the energy and density that is going to be produced by each of these terms. As we know, in electromagnetic fields, we can say that the energy density S is going to be proportional to the electric field squared. And analyzing the different terms of the expression, we can see that the two first terms of the expression are going to produce an energy density that is proportional to 1 over the distance to raised to the fourth exponent. So these two terms are usually known as the near field generated by the particle. And because this energy density generated by these two terms follows this expression is proportional to 1 over the distance raised to the fourth exponent, this means that the energy density generated by these two terms is decreasing and decreasing with the distance very quickly. So at a given distance, they are going to be almost negligible. So these terms that correspond to the near field are terms that, of course, carry energy with the particle, but they are fields that are surrounding the particle, are close to the particle, and as the particle moves, these fields are also moving with the particle, but they are not getting very far from it. So they can also transport energy, of course. This energy can be transferred to other systems, and if it is not transferred to other systems, it is going to be back into the particle. So the energy related to these terms is similar to the reactive energy in a capacitor or the reactive energy in an inductor. If this energy is transferred into other systems, is for example the case of a transformer in which part of the energy of the magnetic field is transferred into the secondary, and then finally into the load. But these terms are not radiation. The only term that generate what we can call radiation is the last term related to the acceleration of the particle, and this is known as the far field generated by the particle. And why is this? Because the energy density produced by this term is proportional to 1 over the distance squared. And this means that the energy that is emitted in a given solid angle, as shown here, omega, is going to be always the same. Because, for example, at this distance here, R1 for this area here, we have a higher energy density and the area is small, so we have a given energy going through this area here. If we go a little further, then we have this other area here, which is much bigger, is proportional to the distance squared, and the energy density is smaller because it's also proportional to 1 over the distance squared, but at the end the total energy that goes through this area is going to be the same. So the same thing happens if we want to calculate the total energy emitted by this term from the particle. If we calculate the energy going through a complete sphere surrounding the particle, this energy is going to be exactly the same independently of the radius of the sphere. And this means that this is an energy that is not surrounding the particle, but is an energy that detaches from the particle, goes away, and never comes back. This energy is emitted into the universe. It can be used at any distance from the particle, but is not going to come back to the particle again. And this is the origin of the electromagnetic radiation. And this is also the reason why we can see the stars at night, even though they are millions and millions of kilometers away. The energy density that reaches our eyes is enough to move the charges in our eyes and then give us the light sensation. So summing up, in this presentation we are interested only in the electromagnetic radiation emitted by the particle. So if we are far enough from the particle, we can neglect these two terms corresponding to the near field and consider only the term coming from the acceleration of the particle, which is the far field generated by the charge. And usually far away from the particle means that we are something like a few wavelengths away from the charge. A few wavelengths away from the charge, we can neglect the effect of the near field and we have only the effect of the far field. So this is the final expression that we have to consider in order to calculate the electric field radiated by the particle. And finally, then we can conclude that all electromagnetic radiation is generated by accelerated or decelerated charges. So now we can understand several processes that generate electromagnetic radiation. For example, in the case of thermal radiation, we know that when we increase the temperature of a material, for example, a metal here in the incandescent lamps, the atoms of the material are going to vibrate due to the thermal energy, and this vibration generates an acceleration of the electrons in the atom, and at the end they are going to, in this way, generate the electromagnetic radiation. At low temperatures, usually the radiation emitted by the materials falls into the infrared region of the spectrum, but in the case of metals, we can increase the temperature high enough and get also radiation in the visible part of the spectrum. We can now understand also the perception of the colors of the different objects, because the electromagnetic radiation emitted by the source of light is going into the object. We usually think that this radiation is going to bounce here and then go into our eyes, but the process is not so simple. In reality, what is happening is that the electric field of the electromagnetic radiation is going to excite the electrons in the atoms of the material, so they are going to vibrate at a given frequency, which is the resonant frequency of the material, which corresponds to the color of the material, and then the electrons are emitting back due to their vibration and their acceleration. They are going to emit back the corresponding radiation that we can see with our eyes. Another well-known process of generating electromagnetic radiation is the generation of X-rays. So in this case, as we know, we use a cathode that is going to emit electrons. These electrons are going to be accelerated by this high voltage applied between the two terminals of the X-ray tube. In this part, in this other terminal of the tube, we have the anode, which is a metal plate. So the electrons are going to get a very high speed because they are accelerated with voltages around 60 kilovolts or even higher, and then the electrons are going to collide with this metal plate, so they are very heavily decelerated, and this deceleration is going to produce the X-rays. This type of radiation is well known and it is called Bremsstrahlung, which in German means braking radiation or decelerated radiation. Well, this is all today in this video. In a second part of this presentation, we will deal with the other aspects. We will see how the oscillatory charges behave and what is the radiated energy density and total power emitted by oscillatory charges. And finally, we will talk about the momentum of light or the momentum of electromagnetic radiation in general. Well, I hope that this topic is interesting for you. Please let me know if you have any comment or question, and I hope to see you in the next video. Goodbye now.